everybody, this is Dr. Nigro with the Chem Calculation screencast. This screencast is going to focus more on a skill versus a calculation. And that skill is writing out electron configurations for atoms or ions and filling orbital diagrams for those atoms, looking at those electrons. Now, before you can start, you absolutely need a periodic table. So if you're working on these and you're at home and you don't have one, that's okay. Just go online, look up a periodic table, and they're easy to find. All right. You have to have it though, because filling requires knowledge of where you are on the periodic table. All right. So let's define these two things first. Let's start with electron configuration. All right. So this is a list is not quite the right word, but kind of. All right. It shows, kind of how the electrons in an atom or ion fill in the principal shells and sublevels from the nucleus out to the valence shell. All right, and don't forget the valence shell are the outermost sublevels. All right, now an orbital diagram is a little bit different. All right, so an orbital diagram gives us a closer look at the electrons in the orbitals within the atom. All right, now both the electron configuration and the orbital diagram have to follow a set of rules. So there are 3 rules that govern how we can fill the electrons in to the atom. And, we say fill, but it's just a representation of showing where they go. I mean, if you have an atom of carbon, we're not just loading electrons into that atom. They're already there. We're just showing where they are within that atom. All right, so the first rule we have to obey is called the Aufbau Principle. All right, and the Aufbau Principle is all about energy. It tells us that the electrons fill the lower energy orbitals and sublevels first. All right, so if you're looking at a particular atom, right, and you're looking where the electrons are, you shouldn't see any gaps, right? You shouldn't see that the electrons have skipped over an orbital or skipped over a sublevel or skipped over a principal shell, right? They have to fill from lowest energy out to higher energy, all right? So just make sure when you're writing your electron configurations or filling in those orbital diagrams that you don't have any gaps in there, okay? All right, second is the Pauli Exclusion Principle. All right, the Pauli Exclusion Principle tells us that an orbital can hold a maximum of 2 electrons. And those 2 electrons must have opposite spins. All right, now, the reason for this, if you think about electrons, they're negatively charged. So if you have 2 in proximity to each other, they should repel one another, right? Because like charges repel, right? The way we get around this is the spin. If they're spinning in opposite directions, they're able to coexist within a certain volume of space, right? If they're spinning in the same direction, however, they will repel one another. So you can have a maximum of 2 in your orbital, but they have to be spinning in different directions. So how do we show this? All right, let's say this is an orbital and I have two electrons in it. I can show them with opposite spins by having the arrows pointing in two different directions. So that would be okay. All right, what I can't do is add a third electron, because if I put a third one in there, it's got to be spinning in the same direction as one of the other two. All right, so those will not coexist. I also, whoops, cannot put two electrons in an orbital and show them having the same spin, because they also will not reside in that space together. All right, so when filling in your orbitals, you have to have electrons, maximum of two opposing spins. All right, and then our final rule is Hund's rule. Right? Hund's rule says that when filling these orbitals within a sublevel, you must fill each, then pair. All right, so what does that mean? All right, it means that because those electrons are negatively charged, if they have a choice, they would rather be in separate orbitals rather than paired, right? Which makes sense, because energetically they don't have to exert, well, they don't exert energy on each other, but energetically it's more favorable, it's more stable for them to be separated, all right, because of those opposing charges. So if I have two electrons to put into a p sublevel, I'm not going to pair them, I'm instead going to spread them out. All right, if I have a third electron come in, I'm going to add it to the third orbital. Now, once I reach the fourth electron, I don't have a choice. I don't have another orbital to put them in. All right, so I'm going to put the fourth electron in the first orbital, but I'm going to put the opposite spin. Then do the same with the fifth, and then the sixth until everything's full. All right, now, don't start putting 7, 8, 9 electrons in a p orbital. They can only have 6. Remember, maximum of 2. Okay, so those are the rules that govern electron configurations and orbital diagrams. Now, rules 2 and 3, Pauli exclusion and Hund's rule, they only show up visibly in the orbital diagrams. You're not going to see them per se when you write an electron configuration. You just need to visualize where these electrons are within the atom when you think about the orbitals. All right, so let's go back to our electron configuration. What does that look like? All right, unlike having boxes and arrows, we're just going to have letters and numbers. So let's say we have a 1s2. All right, the 1 out front, the large one, tells us the principal shell. The S is the orbital, and then the superscript, is the number of electrons in that sublevel. All right. Now, remember, when we learned about principal shells and sublevels can have a certain number of orbitals. Well, sorry, let me back up. Principal shells can have a certain number of sublevels. Sublevels can have a certain number of orbitals, and orbitals can have a maximum of 2 electrons in each, per the Pauli exclusion principle. All right, so that limits what we can do in terms of the subscripts and the sublevels within the principal shells. All right, so for the principal shells on the periodic table, each period is a principal shell. So if we number down the side, that's going to tell us what the principal shell is for that particular row. All right, within the periodic table, we can see that there are kind of blocks, right? There's this block. All right, see how there's empty space next to beryllium, magnesium, all right? Then we've got this block. All right, you can see again the gap between these two, all right, which leaves us with this middle block. And then finally down on the bottom, we have this block. All right, so the periodic table actually breaks up into what are called sublevel blocks. All right, now, I don't know if you guys remember, but I'm going to put this. Let's just do it here. S sublevel has 1 orbital. Hold on, let me slide that over. Oh no, I know what I'm going to do. Hold on. Just need to make myself some room. I'm gonna move more than I want, and that's okay. Fix this. Okay. All right, so the S sublevel, one orbital, which means a maximum of 2 electrons. All right. The P sublevel has 3 orbitals, 6 electrons. The D sublevel, 5, you can see how the orbitals go up by 2 each time, so 10 electrons. And then an F sublevel has 7 orbitals, so 14 electrons. All right, and if we look, you need to think about these elements as you move across the table. Each step, each column you move across, you've added a proton and you've added an electron. All right, so if you go from lithium to beryllium, you've gone from 1 electron to 2 electrons. All right, that block is called our S block. All right, if we move across to boron and we count across boron to carbon to nitrogen to oxygen to fluorine to neon, that is 6 electrons wide. All right, so that means that this is our P block. All right, if we look down at scandium and we move across to zinc, that is 10 elements wide, that's 10 electrons, that's our D block. And then if we look down at the bottom from cerium all the way across to lutetium, all right, that is 14 elements long, that's 14 electrons. This is the F block. All right, so the periodic table is actually written with these electron blocks not in mind, it's just the way the table worked out. All right, so we need to keep that in mind because we can use the periodic table just like a book. We can start at the beginning, hydrogen, and move across the blocks and then down to the next row, across and down, across and down. And we just fill electrons by principal shell, sublevel, and then electrons as we move across until we reach the element we're looking for. All right, now a couple things to keep in mind. Helium. All right, helium in this instance should be over here next to hydrogen. All right, it's part of the principal shell 1 and it's in the S block for this purpose. All right, now when we talked about principal shells and what sublevels were allowed, we learned that at principal shell 3 is the first time we were allowed to have a D sublevel. So even though scandium is in row 4, it starts with 3D. All right. Same thing when we get to cerium. All right. When we get to principal shell number 4, it's the first time that an F sublevel is allowed. Right. So even though cerium, which technically belongs up here, all right, begins or first shows up in row 6, cerium starts with 4F. So it's 1S, 2P, 3D, 4F for the first principal shell for each of those sublevels. All right, so you just need to keep that in mind when we're working across. All right, so let's try. All right, first we're going to find which one we're looking for. So iodine, so it's right here. Wow, I picked one that's way down the table to start. That's okay. All right, so let's start at the beginning at hydrogen. So we're going to move across hydrogen and helium. So we fill principal shell 1, the S sublevel, with 2 electrons. All right, come down to the second row. We're going to move past beryllium. So principal shell 2, sublevel S, 2 electrons. We move across. There's nothing in between beryllium and boron. So second principal shell. Now we're in the P block. We move all the way across. So we put all 6 electrons in. Drop down a row to sodium, 3S, all the way across. Big gap, 3P, all the way across, 6 electrons. Now we're in row 4 at potassium, right? So that's principal shell 4, S sublevel, we move across it. And now we hit scandium, all right? So scandium is the D block, but the D block, principal shell 3, D, move all the way across, so 10 electrons. We're back at gallium. Now we go back to 4, P. We cannot put 3P here because we've already filled 3P. All 6. Principal shell 5, S sublevel, fill both electrons in through strontium, go all the way across that D block row, D10, and now we're in 5p, and we count across 1, 2, 3, 4, 5, and there is iodine. All right, now if I add up all of these superscripts, I'm going to get 53 electrons, and if I look, that is what I should have for iodine, so I know I filled them in correctly. All right, so the key here is this D having one below the P and S. All right, so just keep that in mind. All right, let's try this next one. All right, so potassium. Potassium's right here. All right, so we again start at the beginning. 1s, 2. Next row, 2s, 2. We move across that P block, so 2p6, 3s2. Move across that P again, 3p6. Now we're in row 4. Here's potassium. Whoops. S, and then 1 electron. All right, so we add all of those up. Whoa, what happened? We add all of those up, all right, and we have 19 electrons, which is what we should see. Okay? All right, now we're going to do lead. There's lead. Whoa, even lower than iodine. All right, so it's going to take me a minute. So we'll start at the beginning. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. All right, so now we are at cesium. All right, so it's going to be 6s2. All right, and here is where the lanthanides and actinides come in. All right, so we're going to need to have 4f. We're going to move all the way across that row, so 14. 5d, we're going to move all the way across that row, 5d10, and then we're back at 6p, and we come in 2. All right, so this is what our electron configuration looks like for lead. All right, so again, make a note, 3d10, 4d10, 4f, 5d. All right, I know it's confusing, all right, but you just have to practice, okay? Now, if we count everything up, we get 82 electrons, which is what we expect. All right, for the last one, we're going to do tungsten. All right, tungsten is right here on our periodic table. All right, so it's going to look really similar to lead. We're just going to stop in the middle of that D block. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. Now we are going to move all the way across that F row, and now we're in 5d, and we're going to count 1, 2, 3, 4 across. All right, now one thing, these two guys belong right here and here. All right, if you're wondering why it's 4 instead of 3. Okay? All right, so you can see that you have to pay attention when you're filling in these electron configurations, particularly when the D block comes in and then when the F block comes in. All right, remember, they always start one behind the principal shell or the sublevel above them. All right, now, obviously, particularly for lead and tungsten, that was a lot. That's a lot to write. So wouldn't it be nice if there were a shorthand way to do this? And the answer is yes. Yes, it would. And there is. We call it the noble gas configuration. All right, so for the noble gas configuration, you're going to find element on the table and then look at noble gas in row above element. You're going to put the noble gas symbol in brackets and write electron config only for row containing your element. All right, so this is going to basically take out all of the core electrons and only leave the electrons in the row that the element resides in. All right, so if we were looking, for example, at magnesium, let's just do magnesium. I'm going to do the full one, then we're going to do the shorthand. All right, so if I find magnesium on the periodic table, I'm going to change my, let's go with green. All right, here's magnesium. All right, so it's going to be 1s2, 2s2, 2p6, 3s2. So that's the full configuration for magnesium. All right, now what I'm going to do this time is I'm going to go up and all the way to the end, and the periodic table shows me neon as the noble gas. So to write the noble gas configuration, I'm going to say neon in brackets, and that is going to represent this portion of my electron configuration. Because if I wrote the electron configuration for neon, that's what it would look like. All right, so to finish the shorthand or noble gas configuration, I'm only going to write the portion that is not within that core, so 3s2. All right, so this is going to be the noble gas configuration for magnesium. All right, let's try chlorine. All right, here's chlorine. So it's in the third row in the P block. And if I go up a row into the end, I see neon. So I'm going to say brackets neon, and then it's going to be 3s2, 3p5. All right, so that will be the noble gas configuration for chlorine. All right, let's try selenium. There's selenium. All right, so that's in the fourth row. All right, so if I go up a row into the end, that noble gas is argon. All right, then I start at row 4, 4s2. Now the D block is here, so 3d10, and then 4p, and I count across 4. All right, and last but not least, palladium. Where's palladium? Palladium's right here in the D block in row 5. All right, so I go up and over. That noble gas is krypton. All right, and then I start in row 5, 5s2, 4d, and I count across to 8. All right, so you can see that that noble gas configuration is much shorter. All right, however, the rules are the same. All right, if the F block comes in, it's going to be 4F for the first time. All right, and you just need to continue to fill just like you did before. Okay, pay attention though what the problem asks. It may specify which one you need to use, whether it's the full or the shorthand. All right, so last but not least, we're going to look at drawing some orbital diagrams. Now we're not going to draw the whole thing because it gets very complicated. All right, but we are going to draw the outermost sublevels and orbitals. All right, so we'll be using our noble gas configurations. Now, when we draw these, a single box for S, 3 boxes for P, 5 boxes for D, and then 7 boxes for F. You can also use lines if you want. 1 line for S, 3 lines for P, 5 lines for D, 7 lines for F. I like to use boxes. It's just the way I learned, so that's what I do. All right, now remember when filling, all right, you need to put a maximum of 2 electrons, and you need to indicate with the arrow whether they are up or down. You can use full arrows, or you can use these half arrows like I use. It's up to you. But it has to be obvious. You can't just use lines like this, all right? If you use lines, I don't know which way the spin is, and I don't know that your electrons are obeying the Pauli Exclusion Principle, all right? So do not use straight lines. You have to use either half arrows or full arrows as you fill these in, okay? All right, now let's start with magnesium. I'm going to write its electron configuration. So this is neon 3s2. All right, so neon, 1 box, this is my 3s. and I have 2 electrons in it, up and down. So this would be the orbital diagram for the outermost orbitals for magnesium. All right, let's do chlorine. So neon, 3s2, 3p5. All right, so neon in brackets, a box. This is my 3s. This is my 3p. So 2 electrons, and then 1, 2, 3, 4, 5. All right, so you can see that my arrows show that we are opposite spins when paired, and then I have a single electron in that outermost p orbital. All right, for selenium, we've got argon, 4s2, 3d10, and 4p4. All right, so neon, this is 4s. I'll give myself a little more room here on my P. Oh, whoops. I gotta do D first. 1, 2, 3, 4, 5. This is 3D. And then 4P. All right, so I fill in 2 electrons in that S. I have 10 electrons in my D. All right, and then 4 electrons in my P. So I fill each orbital and then pair. All right, so it's going to look like this. And then last, palladium, krypton, 5s2, 4d8. All right, so I come over here, Kr, I have a single box, 5s. I have 10 electrons here. 1, 2, 3, 4d. So 2 here, and then 1, 2, 3, 5, 6, 7, 8. All right, so 2 unpaired there. Okay, so this is just showing you how you can take those electron configurations and show more distinctly where those electrons are. Okay, so you should be able to use the periodic table to fill in an electron configuration, to draw out an orbital diagram for any atom on the periodic table. Okay, for the ions, maybe I'll just do a separate one for the ions. Okay, thank you.